So our last lesson was on shapes. Today's lesson is on polarity, which is very closely related to the shapes of molecules. So what is polarity? Well, polarity is in the name. It means having poles or opposite ends. So the world has a north pole and a south pole. In terms of molecules in chemistry, it's in respect of charge or electron density, where the electrons are. Okay, and covalent bonds can either be polar or non-polar. So remember in the previous lessons we discussed electronegativity. Well, electronegativity is the ability of an atom to attract bonding electrons to itself. So if you remember, fluorine was considered the most electronegative element, meaning that fluorine has the greatest ability of an atom to attract bonding electrons to itself. So every atom is neutral, number of protons equals number of electrons, but the positive nucleus attracts bonding electrons depending on the amount of positive charge on the nucleus of the atom, so the larger the proton number, and also the radius of the atom. Again, how many electron shells there are. Okay, so this is a section of the periodic table and looking at the different electronegativities of different atoms. So the larger the number, the more electronegative the atom is, the smaller the number, the less electronegative. Okay, so remembering that electronegativity is the ability of an atom to attract electrons, pause the video now and just consider why certain atoms have higher electronegativity than other atoms and also the trends in the periodic table. Okay, so welcome back. So as you can see, as you increase across the period, the electronegativity increases. It goes from 1 in lithium to 4 in fluorine, for example. This does kind of make sense because as you move across a period, the amount of protons increases, the amount of positive charge in the nucleus increases, so electrons are going to be attracted to that because they're negative. Also, you'll note that the increase also happens up a group. So for example, potassium is 0.8, hydrogen 2.1, chlorine 3, fluorine 4. Again, makes sense because as you move up a group, the electrons are getting closer to the nucleus, less electron shells, so again, more attraction, more affinity of the electrons for the atom's nucleus. And as you can see, fluorine has the highest electronegativity. So polar bonds. Polar bonds occur because the more electronegative atom has a greater attraction of the electrons compared to the other pair or the other atom in the bond which they're sharing electrons with. So this means it leads to one of the atoms having slightly negative charge and the other atom having slightly positive charge because the electrons are moving towards one of the atoms over the other. So here's an example here of hydrochloric acid. So from our previous table, we know hydrogen has a lower electronegativity than chlorine, so the electrons will tend to move towards the chlorine. So it will get slightly negative. And because it's losing electrons or negative charge, the hydrogen will become slightly positive. So you must consider the bonding associated with ionic and covalent to be like a continuum, a spectrum. So calculating the electronegativity difference between two atoms will tell us if the bond is ionic, polar covalent, and non-polar covalent. So for example, if it's less than 0.5, it's going to be non-polar covalent. Between 0.5 and 1.6, polar covalent. And if it's greater than 1.6, it's going to be ionic. So in terms of dipoles, so what is a dipole? A dipole, because a bond has a positive end and a negative end, it's said to have an electrical dipole. Okay, di means two, and pole means you've got a positive and negative charge at each end. So for example, here with the hydrochloric acid, you've got a dipole with a positive hydrogen end and a negative chlorine end. And the direction of the dipole is from positive to negative because that's the direction the electrons are moving. There we go, there's the arrow. So polar molecules. So many molecules contain more than one bond, and each bond may or may not be polar. Sometimes the dipoles will balance out, and sometimes they'll form a net dipole in one direction. So a molecule with a net dipole is known as a polar molecule. So how do you predict this polarity? Well, Molecules with one bond are easy, like hydrochloric acid. If the bond is polar, the molecule is polar. So hydrochloric acid is polar. There we go, it's polar. In molecules with one or more, with more than two atoms and polar bonds, the molecule will be non-polar only if the polarities cancel out. Okay, so carbon dioxide, because you've got a carbon-oxygen bond, two carbon-oxygen bonds, and they're both polar in opposite directions, the electrons are moving away towards the oxygen because oxygen is more electronegative than carbon. They will cancel out, and because carbon dioxide is non-polar, carbon dioxide is non-polar because the shape is symmetrical, the polar bonds cancel out, okay, because electrons are moving in opposite directions. However, in order to determine for other molecules, you have to identify all bonds which are polar. You have to establish whether the shape is symmetrical, because by and large, if it's symmetrical, it's going to be non-polar because they'll be cancelling out of dipole moments, and decide whether the polarities will cancel. So in terms of the shapes, which is where we came from the last lesson, there's symmetrical shapes and unsymmetrical shapes. Symmetrical shapes can be linear, trigonal planar, tetrahedral, whereas unsymmetrical shapes are bent and trigonal pyramid. So most linear, trigonal, planar, and tetrahedral molecules are going to be non-polar, whereas unsymmetrical shapes like bent and trigonal planar are going to be polar because the dipoles will not cancel out. So here's an example here: carbon tetrachloride. So you've got 4 carbon chlorine bonds. So you're going to have the carbon chlorine dipoles. Okay, you've got 4 of them. Because chlorine's more electronegative than carbon, the electrons are going to move towards the chlorine in 4 directions. Okay, the shape is symmetrical, so that's already assigned for you. The polar bonds will therefore cancel out, so overall the molecule is going to be non-polar. However, we just change one of those chlorines to a hydrogen. Look what happens. So you have now you have 3 carbon chlorine bonds and 1 carbon hydrogen bond. So you've got 3 carbon chlorine dipoles and 1 hydrogen to carbon dipole this time, because carbon's more electronegative than hydrogen. So 2 will cancel out. However, the carbon hydrogen dipole will not get cancelled out by the carbon chlorine dipole. So although the shape is symmetrical, the polar bonds do not cancel out, so therefore the compound is polar. So let's look at another example. Ammonia. Again, you've got 3 NH bonds, so you've got 3 NH dipoles with the electrons going toward nitrogen, which is more electronegative. So looking at the shape of the molecule, you can clearly see that 2 of the dipoles will cancel out, but there is a third, because the shape is unsymmetrical, the dipoles won't cancel out, the compound itself will be polar. Okay, so in conclusion, here is a short summary of how you can work out whether something is polar or non-polar. So if the bonded non-metal atoms are identical, it's going to be a non-polar molecule because the atoms are all identical. If the bonded non-metal atoms are different and there's no electronegative difference, you've got non-polar bonds, again, non-polar molecule. If there is an electronegativity difference between the atoms, you've got polar bonds. If it's symmetrical, then it's going to have the polar bonds cancel to give a non-polar molecule. And if the polar bonds are symmetrically arranged, but the polar bonds do not cancel, you get a net dipole and you get a polar molecule. So hopefully that diagram here helps in your understanding of whether a molecule is polar or non-polar from the dipoles and from the shapes.